Okay, this is Calc 2, Lecture 7, Integration Techniques, Integration by Parts. Each lecture is just on one technique. So this today it is integration by parts. That is an amazing method. Lots and lots of interesting problems can be solved using integration by parts. Now, integration by parts is kind of the opposite of, say, the product rule. And the product rule is usually one of those rules that students make silly mistakes when they apply it. Recall from Calc 1 that fg prime is fg prime plus gf prime. It is not f prime g prime. Please, please, please. It is not f prime g prime. Now, since we will be using this one too, I have written it u v prime, and u and v are functions of, say, something, x or t or something. So, if I integrate this one, both sides, I have integral fg prime dx, and this is fg prime dx plus gf prime dx. And this one is prime, so that is derivative integral. Derivative integral will give me the function back. So, and I don't need a constant because I still have another integral here. So if I solve for this one, say, it is fg prime dx equals fg minus integral gf prime dx. Now let's look at this. Then I will come back to this, the other one, which will give me another formula. So let's look at this thing and see what is it? What is it good for? So let me write it up here. And so if the integrand is like this, you have a function f and another function which you can just look at it as another function, but it can be derivative of a function g. So if you have a function and derivative of another function, you can integrate this, and the integral will be f times g minus gf prime. Now, why is it important? It might be that this f, when you integrate, when you differentiate f, you get a simpler function. Just imagine if you have like a polynomial of degree, say 5, the derivative of that is, say, a polynomial of degree 4. So that is a simpler function. One of the functions that becomes so simple is ln. The derivative of ln is 1 over x. You need a calculator to find ln, but 1 over x, well, if you know how to divide, you can find it by hand. So, and ln x is a transcendental function. 1 over x is simply the simplest, maybe, rational function. So, if it happens that when you find the derivative of f, you get a simpler function, then use this. In fact, you use it anyway when you see something like this, that there is a function and another function which is derivative of something. So if you see that, then you use this formula, the integration by parts formula. Integration by parts. Oh, now, another formula which is interesting to look at. The other one was u, v. In fact, let me use d. Yeah. duv is u dv plus v du. Right? Now, what is duv? That is like the derivative, right? So I'm using differentials rather than derivatives. So if I integrate this, it's like integrating the other side. And this gives me integral of u dv, and this is simply uv, you know, d and integral, they cancel out. So I have uv minus integral v du. I will, when I solve problems, I will put each one of them in both say formats. I prefer this format. It's much easier for me. I studied Calc 2 a long time ago, and that was the format we used back then. Anyway, but if you don't understand this one, you can use this. But eventually, you have to understand the other one. When it comes to differential equations, you have to be comfortable using differentials. Okay, so there's nothing, no special theory here. It's just basically a simple integration, except this amazingly simple formula can solve interesting problems. So, these are in fact crucial examples. One is the integral of x e to power x dx. Well, it can be x e to power something, kx, but let's just try the simplest one. If you look at this, you might say, okay, there are two functions multiplied, and it's the product of two functions, and maybe you have an inside function. The inside function is this x. Inside function being x is not so nice. But do we have derivative of x here? Derivative of x is 1, not x. No. So integration by substitution doesn't work. Then I come down and say, gee, this looks like f g prime. And so which one should I take as f, which one as g prime? And I said one thing, that if we find the derivative of f and that becomes much simpler, then take that one to be f. So which one should I take to be f? Let me find another color here. Well, I have some blue ones. So, the question is, should I take this one to be f or this one? Okay, which one has a simpler derivative? The derivative of x is 1. That's quite simple. The derivative of e to power x is e to power x. No change. So, this one changes. This goes from x to 1. So, let this be f, and this one g prime. Okay? So, this is f, and I need the g here. What is g? G is antiderivative, and the g will be e to power x. Right? So, the solution is simply, it was fg, let me write it, minus integral g f prime dx. So that is integral fg, or c. So it is, say, x e to power x minus integral g is e to power x f prime 1 dx, right? So it is x e to power x minus integral e to power x dx, which is x e to power x minus e to power x plus a constant. Okay, so that choice, choosing the correct one, is crucial here when you are doing integration by parts. Okay, so now if I have e to power like kx, again the same thing works, except so you have to be careful. If I have e to power kx, be careful when you find antiderivative. So x e to power, say 3x dx, say, then this is f, that's true, and this is g prime. But what is g? G is antiderivative of this. Be careful when you find antiderivative. That's 1/3 e to power 3x. Right? Some students mistakenly find the derivative and they write 3 e to power 3x. No, antiderivative. So in this case, I have 1/3 x e to the power 3x minus integral gf prime, so that is 1/3 e to the power 3x times 1 times dx. So that's 1/3 x e to the power 3x minus 1/9 e to the power 3x plus a constant. Okay, so be careful if you have I have seen a lot of mistakes when it comes to this. The rest is okay. I have seen students, they are quite capable of doing integration by parts, except this thing here is crucial. Be careful when you find antiderivative. You're finding antiderivative, not derivative. Okay. Okay, so let me write another one. So that was one of the most important integrals that you can use integration by parts to solve. The other important one is simply x, say, cosine x dx. E to the power x and cosine x and sine x are quite related, so maybe at some point I will give you some formulas relating them. But anyway, so the same thing happens. There is an inside function, but the derivative of this x is 1, not x. Then I have to choose which one to be f, this one or this one. The derivative of this is 1, the derivative of this is minus sine x. Right? Minus sine x and cosine x are basically the same thing. They have the same, say, level, say. So, well, when you see x, that's the simplest. So the derivative of that is this one. So let's take to be f, this one to be f, and this one to be g prime. And this gives me g equals, that's antiderivative of this, which is sine x. Not derivative, antiderivative. Antiderivative of cosine is sine. Derivative of sine is cosine, right? But the derivative of cosine is minus sine. I know it looks like this, but it has a minus. It has a minus. So this will be x f g sine x minus integral g f prime sine x times 1 times dx. Well, which is in fact integral of sine x dx. So it is x sine x minus integral of sine x is minus cosine, minus cosine plus a constant. So it is x sine x plus cosine x plus c. Okay, so that's another one. You can guess that x sine x also can be solved using integration by parts. So x e to the power x, x sine or cosine x, these are the two important ones. Now what is another one? Trig. So I need the whole, say, whiteboard for the third one. So number 3 is this. Integral e to the power x, say cosine x dx. Now this is this one or this one? Well, derivative of e to the power x is e to the power x itself. Derivative of cosine is a minus sine, almost the same thing. So no difference. So let's take one of them. So let's take e to the power x, okay, to be f, and this one to be g, prime, and g is sine x. So this becomes e to power x sine x minus integral sine x e to power x dx, right? Gf prime. And you say, gee, we just got the same thing, almost the same thing. Yeah, well, that's true. E to power x sine x minus integral e to power x sine x dx. Well, sometimes we need more than one integration by parts. So let's do it again. F g prime, g is antiderivative of this thing, which is minus cosine x, right? Minus cosine x. So this gives me, well, let me continue here. So I have e to power x sine x minus this. So let me put it in brackets. So it is fg, that is minus e to power x cosine x is minus. Minus integral minus cosine x e to power x dx. But let's get rid of this bracket. Minus minus is plus, and this is minus minus is again, and I have minus minus minus, that's minus integral e to power x cosine x dx. Okay? So what is equal to this? I have this integral e to power x cosine x dx equals this. Well, I have both of them. So let's solve for this. Bring this here. Bring this here. If I do that, I have this. 2 well, I should have written some constant somewhere. So that is e to power x cosine x dx will be 1/2 e to power x sine x plus cosine. Well, one of those integrals I needed a constant, so let's just write the constant. So that's it. So sometimes I need more than one integration, and so we have to do it. We have to do 2 integration by parts to find the solution. So well, let me double check and see if I didn't make any mistakes. This is e to power x minus sine x, so that's e to power x minus cosine x and minus minus minus. I think it's correct. I will check that after this. So, and you can guess e to power x sine x should be something similar to this, and you have to do it twice. Now, let's go back to the first integral, e to power x dx. I use that fg prime format. Let's write it in the other format. That was fg prime format. Now, g prime dx is d of g, in fact, right? dg by dx is g prime. So remember, you can just take this as a fraction. So dg is g prime dx. So if I move to u and the v, the other format, this is u, and this is dv. What is v? V is that g. So this equals x d e to power x. This is x d e to power x, and that is with the same thing. Remember, u dv is x e to power x uv minus integral e to power x dx. V d. Okay. So this format, as I said, it's much easier for me. I immediately find in my mind, oh, well, on scratch paper maybe, the antiderivative of this and write it as d of that antiderivative. So for example, this one, x e to power 3x dx, I would write it immediately as x. This one is dv, so it is d of what? It's d of 1/3 e to power 3x. So that's u dv. That's u dv. So it's x times 1/3 e to power 3x minus integral 1/3 e to power 3x dx. Okay? Or the last one was e to power x cosine x dx. You can write it in the other format. It is e d of sine x. See, this is dv. So it is e to power x sine x minus integral sine x d of e to power x minus sine x d e to power x. What is d e to power x? D e to power x is ex dx. Remember, d of u is u prime dx. So that's it. So that's the other format, the udv format. If you get used to this thing, this is much simpler than the other one. But you have to have enough experience with antiderivatives. So immediately you say, okay, I know this is the derivative of sine. So you just write sine here. Okay, so what else? So what is, there are some other nice integrals. So that was number 3. Number 4, the integral that is, let's find the integral of ln x dx. You look at this and say, gee, this doesn't look like two functions. Well, yeah, it looks like that. But how about the other format? How about the other format? u v, u dv. Remember, that was u v minus integral v du. So that is u dv, so that's x ln x times x minus integral x d of ln x. So that is x ln x minus, what is d of ln x? That's 1 over x dx minus integral 1 dx. So it's x ln x minus x plus a constant. Well, you might say, I don't like this thing, so I like f g prime. Well, if you like the other format, you have ln x, you have 1 and dx. F g prime, g is simply x. Okay? There is another function, and that function is the constant function, 1. You don't see it, you don't write it, but it's there. So this is the other format. It's the same thing. It will give me fg, which is what? X ln x minus integral g f prime. gx f prime dx. That's the same thing. So either format will give you the same thing. In fact, it should be the same thing, in fact, not different things. What else? So this really works if the derivative of a function is amazingly nice. What other functions have amazingly nice and much simpler derivatives? What transcendental function has amazingly nice derivative? But this is one of them. The derivative is simply a rational function, 1 over x. What is the other one? Think. Maybe we can use this method of this and a 1 here. This thing can answer. Well, the functions that you know and you have studied is one of them. So, ln, you know, ln, sine and cosine. But ln, we did ln, sine and cosine, no way. The derivatives are almost the same thing. What else? We have, how about inverse trig functions? Tan inverse, my favorite function. Tan inverse, what's the derivative of tan inverse? Well, if you don't know it, tan inverse x dx. Okay, then if you use u dv or you use this method, so let me write it here again. I prefer the other one, but anyway, so if you write it like this, tan inverse of x times 1 times dx, so you will get 1 is what? This is f, g prime, g is simply x. So you get x tan inverse of x minus integral g of x. X, derivative of this. Derivative of this is 1 over x squared plus 1 dx. So this one also the same, u, v, so that's x tan inverse of x minus integral x derivative of tan inverse of x. So that's x tan inverse of x minus integral x times 1 over x squared plus 1 dx. Okay. So x and of g, an inverse minus, well, let me just write 1/2 integral 2x over x squared plus 1 dx. Now recall, I'm not sure why, I think I did that in the first lecture, that if integral of, say, f prime x over fx dx, by substitution it is ln of absolute value of fx. Let's see. This is the same thing. F prime. So I have x tan inverse of x minus 1/2 ln of x squared plus 1 plus the constant. So, yeah, you might say, gee, the derivative of such a nice and tiny-miny function is this. Yeah, sometimes the derivative of a tiny-miny function is like 3 lines. I mean, integral, antiderivative. Yeah, the antiderivative of tan inverse has a tan inverse and also an ln. So let me write another one. I'm not going to solve it. I leave it to you. And that is, you might guess, that is sine inverse. Is it 6? 4, 5, 7, I guess, right? So next one is, as you can guess, it is sine inverse. So that is uv, so it is x sine inverse of x minus integral x derivative of sine inverse. What is derivative of sine inverse? Well, let me write it for you. So I have x. In fact, let's write it like this. Well, I leave the rest to you. That is integration by substitution. It's not ln. Please, please, please. ln is only when this whole thing, the derivative of this whole thing is here. Not the derivative of the inside function. This is the inside function. So I leave that to you to find this integral. So if you write u for that, then you have u to power -1/2 on top, times d or something like that. So anyway, let me stop here, and next time I will discuss another integration technique.